Good morning, everybody. Actually, afternoon. Today, I have been working on that same frontal to sagittal hip joint. And what I'm working on with that is how to house these exomuscles that have 20 tons of force. 20 tons of force trying to bend it and break it in half. And what I've realized today is that I'm going to go back to using a composite, which was one of my initial ideas. It's going to be a Kevlar composite, which will have very high strength, even higher than titaniums and high strength steel alloys. Very, very high, especially in tension, a little bit less in compression, but about the same compressive strength as titanium, about twice the tensile strength. Fusion 360 can't really do that, so I use titanium as a replacement to that because it's actually even stronger than titanium, so I just use titanium type 5 alloy as the tensile strength, as the material, as a stand-in. It's not perfect by any means, but as long as we get pretty close, the composite will actually be stronger. So I worked on that, and then I've also been brainstorming today. What I want to do is I'm building a file just to do a simulation on that part that comes back off the shoulder, and that the pec muscle that will go from here to here, be pulling on it. I want to see how that affects all that structural part, because that's 5 tons pulling the shoulder girdle forward, so I want to make sure I can build this back piece strong enough to be able to handle that load. So yeah, that's what I've been working on today. I haven't gotten anywhere on the back part yet, so I don't have anything to show you guys on that, but what I am going to show you is this hip part, which is pretty crazy, because remember, this part is going to be about as big as my hand, like that, about that thick. It's going to be a part that goes around like this, and it's literally going to have 20 tons of force pulling in it. So what happens on it is there's 20 tons of force pulling this way and then this way, and then they're wrapping around to you, and there's 20 tons of force going in that way as well, because that's how the math works when it wraps around like a rope like that. So there's 20 tons trying to bend this thing around. So keep that in mind. This is a little tiny part we're talking about that's going to have 20 tons is half the full loaded weight of an 18-wheeler. So half of an 18-wheeler, like a rope essentially being tied to that and then just holding it, and it'll just stay, it won't break. Half of an 18-wheeler. You could hang, so you had 2 of them, you could run a rope through both of them. So that would be how it would be with both sides of the pelvis. You could take 2 of those, run a rope through them, Kevlar rope, tie it to the end of an 18-wheeler and pick it up, and it wouldn't really deform the pieces that I'm designed. How about that for a visual? Let me go show you how it works. So guys, here's the model. So this piece right here, that piece is, so here is the pelvis, that's me in it, and then that piece is this curved piece that goes right here. So this is the old one, and then I'm going to show you guys the new design. So that's this right here, and these are the joints. So this one would be the one that's actually on the pelvis, and then this one comes around, and this would be the one that's going down the leg. So I don't have my body actually in this one, but this is a cross section. That would be like my hips right there, and then if I was like this way, I would be, my groin would be down here and my head would be up here. This would be facing in from the front. So then there is one mount here for exomuscles, and that one has 4 tons of force pushing on it, and then these each have 2 muscles going down the front and 2 kind of coming down this, so 2 down the front of the center of rotation and 2 down the back of the center of rotation. That's why there's 2 different parts there. And then each of those in the simulation had 2 tons on them. So remember, each exomuscle has 5 tons, and there's 4 muscles running through this thing. So this grayer, this darker metal, that is the titanium right now. But I'm actually going to change the color of this to look like a plastic, because this is actually going to be, we'll actually do a light brown fabric. Look at that. It looks like composite. That works. Okay, that's actually what that'll look like. So it'll be a plastic part that's 3D printed, and then there'll be a composite over the top of it like that. So I'm using the tensile strength of titanium to test it. And so the muscles, remember, they'll come down like and around this part here, and come like around, all the way around in different parts. So like if you look here, these are all, this is that part is right here and right here. That part is right there, and these all run down in and around that center part, which is right there. So those all run around and then come through, and then they'll run down the leg like that. So this is a compartment, and there's actually going to be muscle bellies inside this thing that contract, and somehow there'll be plumbing going in there, which I got to remember. I got to figure out how to do that too. But there's going to be plumbing going down in there and then actuating them with hydraulic force. So anyway, here's the simulation for that. Oh, and then on the inside, let me show you. And then on the inside, there is like still aluminum struts. You can see they're there. So those will be built into the composite, and they'll actually be covered in composite. But then I'll actually have some really high precision metal parts that I can weld all this together first, and then make the composite out of it after that. And then there will have to be a seam going down here. So there's going to be a clever way that this thing is actually going to bolt together in two different parts. So that also has to be figured out with this. But this is a more simplified version of that, so I can figure out how I can do that. And you'll notice that all the composite is on the outside and all the aluminum is on the inside, because the strength of a pipe is mostly dependent on the strength of the skin. So you want the highest strength stuff on the outside, so you're actually going to make the composite all on the outside and essentially no compositing on the inside, if that kind of makes sense. This is just how you design composites. That's why they're strong, is because the skin of them is strong. So there's aluminum running through there, so I have parts to build off to, and then I'm going to 3D print into the gap. I'm going to 3D print parts and glue it all together, and then wrap it in this, like that. And then there's also a metal part that slides in the middle of here, and that gives just a very solid mechanical spot for that to kind of fit on to start with. And then kind of composite reinforcement on the back. And then here's a simulation on that, so you can see it actually works out pretty good. Don't worry about this in here. That's a low-strength material. This could actually be made out of real titanium if it needs to be, because right now it's made out of aluminum, and it's really not bending that much anyway. There's a lot of red in there, but it actually wouldn't bend all that much. So the aluminum itself would probably work, but I can use titanium in the actual model if I need to. So I'm not worried about the red on here. So if you ignore the red on here and you look, really the only spot there's red is like right in here, and it's just a very small amount, and that's really nothing to be worried about. One thing that's cool, if we look, that's the safety factor over here. If you look, this is where the stress is occurring, so it's occurring right in there. And then you'll see the displacement. I was holding this side still and putting the load over here, and you can see how much it moves over here. And it's actually, this is the actual calculated movement of this thing. But the thing is that actually probably won't happen, because I'm going to be using a composite, and composites really don't bend very much at all, so it'd probably be a lot more rigid than that. It's a lot stiffer than that, so it's higher stiffness than titanium is even. So it'll actually be even stiffer than that. So it actually will probably stay locked in that spot. And then if it fails like catastrophically. Instead of just bending, it'll go and break. That's just how they fail, but it's not going to fail. So. Alright guys, I hope you learned something about composites and how those work. The skinning effect is it's the reason that composites work. And if you look at like a solid metal bar versus the strength of that versus a tube, the strength is almost exactly the same. But obviously the bar weighs a lot more. That's true for like even really thin bars. So it's an important thing to consider, and it's actually one of the kind of at the heart is that skinning effect is kind of at the heart of the dual exoskeleton design. It's kind of making a tube all the way around me. That kind of makes sense. So that's why this thing is so strong and able to handle the loads that it does. It's just that the huge loads that this thing puts out is a little too much for that one part, so I'm going to have to switch over and reinforce it with composites. And then I may have to do some of that stuff in the shoulder as well, where I have those really high loads on there, but that should hopefully be it. Hopefully I won't have to do that in many other places than those. So just those couple of spots where there's like tremendous force in between those muscles. Mostly in I was actually expecting it more so in the shoulder, but I kind of didn't fully consider how much force is being channeled to that one little tiny tube in there, and so that part ended up being kind of complicated too. So I am a little bit worried about this shoulder, but it's a lower load overall being placed on it because it's only one exomuscle. But it's a little bit larger moment arm, but it's a much smaller load. So I'm not I'm not sure. Yeah, I'm not sure. That's why I'm building that simulation first, and so hopefully I'll get an idea of how to do that, and then I can figure out how to build it for real. But that's why I'm kind of starting with like just a very mock-up, and then I'm gonna run some simulation tests on it until I start to figure out what I want to do, and then I'll spend all the time to actually make the full exoskeleton from that, and that'll hopefully make things run a lot more smoothly, and really help me figure out how these exomuscles are gonna go in there for draft 4, and I can build that out, and then once I get all those ideas out, then I'll do that draft 5, and we'll build draft 5. You guys are awesome. If you're seeing this video for the first time, smash the subscribe button. It really helps me out. And the rest of you lovely bastards, come back tomorrow. I love you.